Hey, this is Horner, and this is the Rotational Energy and Momentum review question number F2. This is for the baseball and softball players. A student studying studying the game baseball, wishes to determine the rotational inertia of a baseball bat. It is rotated about its axis. It passes through a batter as the batter swings to hit the baseball. So they want to know, how do we find the center of mass? It's pretty easy to do. We just balance the bat on a pivot. In fact, if you put your fingers on either side of the baseball bat and then slowly move your fingers towards each other, your two hands towards each other, you will stop where that bat balances. That would be hard to explain here, so you can just say you just need to balance the bat on a pivot or a fulcrum, and where it balances is the center of mass. So if you're doing points here, this is a point, and then mentioning the center of mass is a point. If we move on down, the student's research indicates the batter holds the handle at a distance of 0.9 meters. So if you think about this length here, the student's experiment will determine the rotational inertia of the bat, and it consists of this setup. There's a light rod that is 0.9 meters long. It's glued to the handle of the bat, and the other end is connected to a frictionless axis. So this is that axis, and this is kind of mimicking the arms of the person. The assembly is allowed to rotate in the vertical position, so it starts here, has potential energy due to gravity, and then that is converted all to kinetic energy. Oops, that's supposed to be a K. So that is converted to kinetic energy down here at the bottom. You'll see there is a height change from here down over to where this is. So they want to know, let L represent the distance from the handle end to the bat's center of mass. And that's where it's going to rotate about. That's where if you threw the bat, it would spin about that center of mass. They want to know, what measurements must the student make in order to calculate the rotational inertia of the bat about the axis. So here we know rotational inertia is going to be some sort of form of mr squared. And if we went back and looked at our equations, you would see that it would be similar to a rod that is rotating about its end. So it would be 1/3 ml squared, and that's the length. Let's go back here. It says measure the height of the center of the mass, here, down, and we'd use a meter stick to do that. We would then record the bat as it's traveling from here all the way through, and we would calculate what that video would tell us in terms of how fast it's going at the bottom. Or probably an easier thing to do would be use a photo gate. And you basically put one photo gate here, you put the other photo gate here, and then you have a beam going between the others. Or you could put a laser here, and that laser would shine through to this, and then as the bat would pass by, you could find the velocity of the bat. So find the mass of the bat using a scale. Now they want us to explain how the measurements can be used to calculate the rotational inertia. So to do that, we're going to do this, and we're going to say, using the data from the photo gate, we can find the instantaneous velocity. So there's our V. We can find the angular velocity by saying, well, we know that velocity is equal to angular velocity times r, so butt is equal to v over r. And then we're going to use conservation of energy, which is mgh, and that's equal to the rotational kinetic energy, which is 1/2 I omega squared. We're going to solve for I, and m is the center of mass. So as long as you say those things, you will get full points for this. Now we're going to consider a batter swinging the bat and striking a pitched ball. Just before the bat hits the ball is moving horizontally in a direction perpendicular to the bat's length. So we know that, here's your ball, it is moving in this direction, the bat is swung, and then you hit the ball. So here's the handle of the bat. You hit the ball, and they have a really nice 90-degree angle here. Consider the system of the batter, the bat, and the baseball. So is the angular momentum of the system the same after the ball is struck as before it was struck? And no. There is got to be some sort of external torque, so the angular momentum is not conserved. So when you hit this, that external torque comes from the air friction with the ball. So as it's coming in, it loses, and as it comes back out, it loses again. Is the linear momentum of the system the same after the ball is struck as before? And again, we can say no. There's an external torque on the system coming from the batter. So if you think about the batter, they're twisting, they have spring energy, and it hits the ball and goes the other way. There's air resistance there, all kinds of things that you could talk about. And that is question number 2.